Hi, good morning. Today we continue with 5.1 gas under topic states of matter, chapter 5. Ideal and non-ideal behaviors of gases. Ideal gas is any gas that obeys ideal gas equation and has properties as outlined by the kinetic molecular theory of gases. Whereas real gas or non-ideal gas, gases which do not obey ideal gas properties. Deviation from ideal behavior. Real gases do not show ideal behavior and said as that they deviate from the ideal behavior. The deviation due to gas molecules do have its own volume and they occupy some space, while there is significant intermolecular forces acting between them. Meaning to say, real gases have volume and have significant intermolecular forces, while ideal gases volume of the gas particles negligible compared to the volume of container, and there is no intermolecular forces acting between the ideal gas particles or insignificant intermolecular between particles of ideal gases. Real gases do not behave ideally because gas molecules have volume. First, we look at the container number 1. And as we increase the pressure or we compress the piston, we can see the gas particles occupy some portion of the container, or we said occupy sizable portion of the container. Therefore, real gases do have volumes. Secondly, real gases also have attractive forces between the particles. As you see in the third diagram, attractions lower forces of collision with the wall. Due to the attraction between the particles, the pressure exerted on the wall is lesser because the intermolecular forces pull the particles or attract the particles to one another. That means there is a significant intermolecular forces between real gas particles. Collision between molecules and the wall of container less frequent, and the pressure exerted is lower than the ideal gas equation. The deviation is more significant at high pressure and low temperature. Now at high pressure, what happens is, at high pressure, gas molecules have volumes, while at low temperature, the particles have significant intermolecular forces. Therefore, at this moment, we say real gas do not behave ideally. Now, what happened at high pressure? The volume of container decreases, thus the molecules are closer to each other and begin to occupy a sizable portion of the container. Thus, volume of gas molecules becomes significant. And as the volume of the container decreases at high pressure, the molecules are close to each other, and therefore the intermolecular forces become significant. Whereas at low temperature, kinetic energy of the molecule decreases, molecules moves at low velocity, then here also the intermolecular forces become significant. So under these two conditions, high pressure and low temperature, real gas do not behave ideally. This is the statement. Real gas do not behave ideally. However, real gas can also behave ideally at the opposite condition of low pressure and high temperature. At low pressure and high temperature, deviations are small. Ideal gas equation can be used without generating serious error because at low pressure, volume of the container is increased. When the volume of container is increased, molecules are very far apart from one another. Hence, the intermolecular forces can be neglected. At low pressure also, the volume of the container is extremely large compared to the size of the molecules. Thus, the volumes of molecules can be neglected as well. Meanwhile, at high temperature, gas molecules have high kinetic energies and move at high velocity. The molecules are able to free themselves from intermolecular forces that act between them because they are moving at a very high speed. Thus, the intermolecular forces become insignificant, or we can neglect the intermolecular forces. At this moment, real gas behave almost ideally. We look at the graph interpretation. We plot a graph of PV over RT versus P, and PV over RT equals to 1 because we take 1 mole as a standard. 1 mole of nitrogen gas, for example, at different temperature. So as students can see, we have 4 different temperature here. As the temperature increases, the line becomes closer to 1. That means the value approaches 1.0 as the pressure becomes very low. Meaning to say, at very low, the gas behaves ideally or almost as idle. And if let's say we take 203 Kelvin, then at low pressure, it is almost ideal, but as the pressure increases, it deviates very far from the ideal gas. Same goes to 293 Kelvin and 673 Kelvin. As the pressure increases, they deviate significantly from ideal gas, because at high pressure, real gas do not behave ideally, which I've explained in my previous slide. Okay, the line converges to 1.0 when the pressure approximately 0. This is what I mean. At very, very, very low pressure, the gas, whatever real gas, behave ideally. The lines approaching the ideal line when the temperature increases. This is another parameter. Compared to 203 and 1000 Kelvin, 1000 Kelvin is much closer to ideal gas. That means gas behave ideally at high temperature.